There's two purposes for this video. I'm going to finish off the 13.5 and 13.6 lecture. I also am going to do number 51 to show you how to work that out. And the big goal here is to work on ice tables and how to solve equilibrium problems. Okay, so we needed to come down here, and if you remember, there were two more conditions for this reaction that we were trying to solve for. So if I look at what they tell me, they're telling me I have 1.0 moles here, 1.0 moles here. It's in a 1 liter flask, so I don't have to do any of that funky math. 0 moles on this side. So I'm going to have minus 2x, plus 2x, and plus x, so that my equilibriums are 1.0 minus 2x, 1.0 plus 2x, and then x. Now if you remember, our k was equal to 1.6 times 10 to the negative fifth, which is small, at least 1/1000th of what we would be subtracting from. So what that means is when we set up our equilibrium expression to solve for x, we've got x 1.0 plus 2x squared over 1.0 minus 2x squared. Where am I getting these from? Okay, remember this is the reactant, so this goes on the bottom raised to the second power. This is my product, it goes on the top raised to the second power. Okay, now from here I can do my shortcut of crossing off the minuses and the pluses because this is so much smaller, right? Which clearly makes my math way easier because I end up with x 1 squared over 1 squared. Okay, so x in this case is going to be equal to 1.6 times 10 to the negative fifth. So you just get x equal to this. Much easier than doing all this hideous math. Okay, so now what we end up doing is solving for it. Well, when you take 1.0 and you subtract 1.6 times 10 to the negative fifth, even times 2, it doesn't really change it. So my concentration of NaOCl is still going to end up being 1.0 molar. Alright, same thing's going to hold true for the nitrogen monoxide. 1.0 plus 2 times 1.6 times 10 to the negative fifth isn't going to have any effect. So my concentration here is going to be 1.0 molar. And my concentration for chlorine is simply going to be equal to x. Okay, so my chlorine is going to be 1.6 times 10 to the negative fifth molar. Okay, now the reason I wanted to cram that in is I again wanted to show you how to do the 5% check. Alright, what we are trying to make sure, right here, and right here really, but it's the same math, is that what we negated, what we crossed off down here, needs to be less than 5% of what we were going to be subtracting it from. So for this particular problem and this particular check, what we needed to end up doing is make sure that 2 times x, or 2 times 1.6 times 10 to the negative fifth, is less than 5% of 1. Okay? So when I do that math, now, you know, pretty straightforward, 1.6 times 10 to the negative fifth, I take that times 2, I divide that by 1 times 100, I'm at like 0.0032%. Okay, so very clearly what this lets me know, and it needs to be, you know, less than 5%, but it lets me know that what the shortcut I took earlier didn't negate anything. So that's how you do the 5% rule. When you do the 5% rule, again, you're just trying to make sure that what we were crossing off, this portion is less than 5% of what we were subtracting it from, and it's not going to change our results. Okay, next one is 2 moles in a 1 liter flask. Again, I've got all the math worked out here. You'll notice that we also here take the liberty to get rid of the subtraction because this number again is so small. X ends up being in this case 0.0040. So when we solve for the actual concentrations for NaOCl, we still end up with again 2.0. Where am I here? There we go. Okay, NaOCl is 2.0 molar. The chlorine again is still going to end up being 1.0 molar. And the nitrogen monoxide is going to be 0.0080 molar. And again, in order to check that, we just want to make sure that what we negated is less than 5%. So in order to come over, I'm going to come up to the top here and check my 5% rule. What I need to make sure is that my x, my 2x, is less than 5% of what we were subtracting it from. So in this case, it's less than 5% of 1. So what I do is I take my 0.0040, and I know for math people this is kind of redundant, but I'm just making sure that it is less than 5%. Okay, and in this case it's only equal to 0.4%, which is much less than 5, so it means that our assumptions and that our checks were good. Okay, so that's the end of 13.5 and 13.6. Big take-home message again is, remember, is you got to know how to set up the ice tables. Once you find x, plug them back in to find the concentrations. The funky part comes in when you have to actually figure out where the x comes from. Alright, let's do this. Now let's talk about 51 here for a second. Okay, for 51, let me scroll down here. Here's 51. 51, yes, it was 3 separate problems, all kind of wrapped into one, which really is very similar to what we just did, which makes sense as to why this video goes together. Alright, you've got 1.6 times 10 to the negative fifth. Calculate the concentrations of all of the species at equilibrium for each of the following sets of conditions, where you have 2 moles in a 2-liter flask, where you have 1 mole and 1 mole in a 1-liter flask, and then 2 moles and 1 mole in a 1-liter flask. Okay, now this is actually the exact same problem that was in the PowerPoint, now that I look at it closely. So I already explained the work for you, but to see it explained again, yes, it would have been 3 separate ice tables, and this just shows you how things are worked out a little bit. It must proceed to products to reach equilibrium since only reactants. So again, one of the tricks for part A, you would have taken 2 moles divided by 2 and get to 1. Here's our K value. You set it equal. This explains the assumption a little bit more. So that if we assume that 1.0 minus 2x is about 1, you can then check the assumption. And to check the assumption, that's kind of what I was doing over here. The error is about 3%. So for example, 2x is 3.2 of 1.0. If the error is less than 5%, then you can go forth and you can solve for it, which is then what they did. They plugged it back in. Okay. Now they just give you the long version right here. It says if we were to solve the cubic equation exactly, a long and tedious process, we would get x equals 0.016. It's the exact same answer. So whenever it's very small, and again I use that 3 decimal place rule, then you can go at it that route. Okay, this is going to again just show you the problems that I just showed you. So, but you've got the 1 molar up here. You've got your x. You're getting rid of the ones that have the subtraction on them. The assumption is really good because the percentage is so much smaller, so you just plug and chug. The NaCl and the NO really stay the same because that x is negligible, but the chlorine is going to be 1.6 times 10 to the negative fifth. And then last but not least here, C again, where you can solve for it. X is 4.0 times 10 to the negative third that we just had written down. And then you go back and then you plug those in. Okay? 0.0. Actually, this one I think was a little different. Last time they gave me 2 moles of this and 1 moles of that. I don't care about that. So anyway, just shows you how to set up 51, ice tables, x values. If you have any questions.